Hello everyone and welcome to lecture 4 of computer architecture. Today we're going to start talking about the fundamentals of logic design. In the first lecture of the course, we looked at the abstraction layers that go into building computer systems. And we said that having these layers of abstractions allows us to build complex systems and to be able to develop each one of these layers independently while not affecting the other layers in the way that they need to be designed, but at the same time benefiting the entire stack when we develop these layers independently. And we also said that in this course, we're going to be looking at these three layers, logic design, which is going to be the first part of the course, the instruction set architecture, which is the interface between hardware and software, and this is going to be the second part of the course, and then microarchitecture, which is the layer that bridges these two layers, and this is going to be the third part of the course. In the second lecture, which was another introductory lecture, we talked about performance, and we gave an example of a car and a bus, and we saw how these two different vehicles, depending on the performance metric, may have better performance. We said that a car might have better execution time in terms of taking one person from one place to another, but if we cared about throughput, if we cared about the number of tasks we want to do in a given amount of time, or the number of people we want to transport in a given amount of time, then a bus is a better option. And having motivated that, we looked at this equation that I would like to ask you to please mute yourself when you enter so that it doesn't bother other people. We looked at this equation and we saw how the execution time of a program depends on three factors: the instruction count, the number of instructions in the program; the clock cycles, the number of cycles it takes to execute an instruction on average; and then the seconds per clock cycle. So this is the period, or the inverse of the clock rate, or the inverse of the frequency of the processor. And we saw the interactions between these different factors, and we saw how the clock rate alone, so having a high frequency processor alone, is not enough for us to have to improve the execution time of a program. We also need to be cognizant of how increasing the clock rate may affect these other factors. And then finally, in the last lecture, we looked at numeral systems, and we saw how, as humans, we're used to dealing with the decimal system, but how with computers, because we usually represent data in a computer and signals as being in one of two states, either high or low. For computers, we like to use the binary numeral system. And we also looked at the octal and the hexadecimal numeral system as other numeral systems, numeral systems that are a bit less verbose than binary, which are convenient to use when, for example, we're writing or reading a textbook. But at the same time, they're easy to convert it's easy to convert between binary, octal, and hexadecimal because octal, which is base 8, 8 is just a power of 2, and hexadecimal, which is base 16, 16 is a power of 2. So that makes conversion between binary and these other two systems easier than conversion between binary and decimal. So with that, what we're going to do today is we're going to begin the first part of the course, which is logic design. We actually began the first part of the course last time when we started talking about numeral systems, because we talked a bit about how about computer arithmetic and how computers do arithmetic, but we talked about it at a high level. And then we will, in this part of the course, get into more details about how some of what we described last lecture are actually implemented in hardware. Does anyone have any questions about what we have covered so far before I start today's lecture?
Yes, Professor.
Yes?
Professor, we used while changing octal, I guess, and hexadecimal to divide them into 3 or 4 bits, which makes converting easier. Yes?
Yes, that's correct.
Okay.
So
Yeah.
binary corresponds to one octal digit,
Yeah.
The fragments of binary correspond to one hexadecimal.
Yes, Professor. While dividing, we add zero at the beginning to make the number divisible by 3 or 4.
Right. So if your binary number is not divisible, the number of digits in your binary number is not evenly divisible by 3 or 4. What you would do is you would add zeros to the left, because zeros to the left do not affect the value of the number. Don't add zeros to the right. If you add zeros to the right, that is the value.
Yes. Okay. Thank you.
Yep, you're welcome. Any other questions? Okay, well then let's get started. So today we're going to talk about logic design, and we're going to start talking about, we said that the logic design layer is about how we can go from logic gates that perform simple logic operations like and, or, and not, to building more complex logic blocks that do more interesting functionality like adding, multiplying, or storing data. So what is a logic block? The computers, we've said before, are built from circuits that can store charge and process electric signals in one of two states, high voltage and low voltage. And from here on in the course, we're going to refer to high voltage signals as representing a 1, and we're going to refer to low voltage signals and low voltage charges that are stored as representing a 0. So with that said, a logic block is a circuit that can perform operations on a set of input signals, which are going to be either ones or zeros, to produce a set of output signals, which are also going to be ones or zeros. There are two general categories of logic blocks that we will look at. Combinational logic refers to the kinds of logic blocks where the output of the block depends only on the current input to the block. And on the other hand, sequential logic refers to the case where the output depends both on the current input as well as values that are stored in the block. So sequential logic, you can think of it as having some kind of memory. So the input I give it the output that comes out of it depends on the input, but also on some value that's stored. If I might give it the same input at different points in time, and it might give me different outputs depending on what value was stored at the point in time when I applied the input. So the focus of today's lecture is going to be on combinational logic. Actually, the next few lectures will focus on combinational logic. And then later on, we will take a look at sequential logic. Okay, so let's talk about combinational logic. I'll start by talking about truth tables. When we want to design a logic block, we would like to specify the behavior of this block. We would like to specify how the outputs of a block are affected by the inputs into the block. And one way of specifying the behavior of a logic block is using a truth table. And I think you guys have already seen two truth tables in CMPS 211. We'll briefly cover them again in this course. So a truth table is a specification of a logic block that exhaustively lists each output for every possible input. So what a truth table does is it has all possible combinations of the input, and based on these combinations, it tells you what the output should be for each of these combinations. So I'll start with an example. We're going to have a running example throughout this lecture. And a running example is going to be a car warning system. So you know how if you, for example, take your key out of the car, but the lights are still on, the car kind of beeps and warns you that something is wrong. Or maybe if you open the door of your car and the key is still in the ignition, the car will beep to remind you not to forget your key in the ignition. This is the car has a circuit that takes care of these things, and we're going to use this as an example to demonstrate the different ways of specifying logic blocks in today's lecture. So let's start with a truth table. Let's create a truth table for this logic block. So when do I want my car to beep? When do I want my car to warn me that something is wrong? So here we have all the possible combinations of these three events taking place, the door being opened, the key being in the ignition, and the light being on. And these are going to be our inputs, and we have all combinations of these inputs. And for each of these combinations, we're going to have a 0 if we don't want the car to beep, and we're going to have a 1 if we do want the car to beep. So here there are 4 cases where we want the car to beep, this case over here, and these 3 cases down here. In the first case, we want the car to beep if my door is closed and my key is not in the ignition, but my light is on. So for example, here, if you park, your door is still closed, you remove the key from the ignition, but you forget the light on. We want the car to beep to warn me that my light, that something is wrong. And then I would check and make sure, oh, my light is on, and I would turn it off. The other case is, and these 3 cases are where my door is open. If I open my door and my key is not in the ignition, but my light is on. So here, if I remove my key is not in the ignition, but my light is on, and I open the door. Here, the car says, well, this person is about to leave the car, but they forgot the light on. So in this case, we would like the car to beep. And the other case is if where I open the door and my key is in the ignition, so I haven't removed the key, which means maybe the car is still on. But in this case, regardless of whether the light is on or off, I would like the car to beep, right? Because if I open my door and my key is still in the car, I want the car to warn me because I don't want to close the door and leave the key inside of the car. Okay, so these are the cases. This truth table specifies the behavior of this logic block. This truth table says, for which of these inputs do I want the output B to be 1? In other case, for which of these inputs do I want the car to be? Okay, any questions? Any questions about truth tables? I think you guys covered truth tables in CMPS 211 before, so I think most of you are already familiar with it. Okay, let's move on. So another way to specify the behavior of a logic block is using logic equations. So logic equations are essentially based on Boolean algebra, which you've probably already seen in CMPS 211 as well. And Boolean algebra, all variables in this algebra are either 0 or 1. So that's why it's a convenient representation for logic blocks, because logic blocks process signals that are either 0 or 1. Yes, question?
In the car warning system logic, we need the car to beep when one of the inputs are true, at least one, right?
No, that's actually not true, because there's this case over here where the system doesn't beep. So for example, here, if you open the door but your lights are off and your key is not in the ignition, that's okay, right? If you park your car, you turn off the lights, you remove the key, and then you open the door to leave the car, that's okay. Here it doesn't need to beep.
It's not only the or.
Right, no, it's not that. It's a little bit more complex, and we'll see later on how we're going to represent this using an equation. Actually, I'm just about to talk about that.
Okay, thanks.
Yep, you're welcome. Okay, so back to logic equations. So we said that another way to specify the behavior of a logic block is using logic equations, and Boolean logic equations use Boolean algebra. So in Boolean algebra, all variables are 0 or 1. And typical formulations, there are different formulations of Boolean algebra. Typical formulations, which is probably what you're used to, have 3 fundamental operators. These operators are the OR operator, which we usually represent as a plus. And here OR means A plus B is 1. So A or B is 1 if A is 1 or B is 1 or both of them are 1. The other operator is the AND operator, which you usually represent as a dot. And here A and B is 1 if both A and B are 1 at the same time. And then finally, there's the not operator, which we represent as a bar over the variable. And here not A is 1 if A is 0. So these 3 operators are enough to specify all the possible operations that we would like to do in Boolean algebra. Any other operator can probably be specified as a combination of these operators. Okay, so let's see how we can specify the car warning system using logic equations. So here what we can do is we can use the table itself and infer the logic equation from the table. So we can look at all the cases where the output is 1, and we can write, this is one way of doing it, by the way, there are other ways, and we'll talk about those other ways later. But here what we can do is we can look at all the cases where the output is 1, and for each of these cases, we can write a term in the equation. So for example, here we can say that B equals, for the first row, B is 1 when D is 0, K is 0, and L is 1. So here we can write that B is not D and not K and L. So in other words, if D here is 0, not D will be 1. If K is 0, not K will be 1. And then L is 1. Here we'll have 1 and 1 and 1, which will give us 1 for B. So this term over here corresponds to the first row. Similarly, for the second row, here we want B to be 1 if D is 1, K is 0, and L is 1. So we can write D, not K and L. Or we want B to be 1 when D is 1, K is 1, and L is 0. This is the orange row over here. So we can write D and K and not L. And then in the final combination, we want B to be 1 if all 3 of the variables are 1. So here we can write or D, K, L. Okay? So here we have a logic equation that specifies the behavior of the block. So there's 2 different ways to do it, either using truth tables or using logic equations. Any questions about logic equations? Again, I think your guys are familiar with this from 211. Yes?
Not D here, you mean it's no, 0?
So here by not D we mean that B is 1 if D is 0, K is 0, and L is 1. Because
So
if D was 0, not D will be 1, and if K was 0, not K will be 1, and then if L is here L is 1. So if D was 0 and K was 0 and L is 1, then not D and not K and L will be 1.
Oh, okay. Okay, thanks.
Yeah, you're welcome. Okay, let's move on. So this is a logic equation. Now, with Boolean algebra, there are many Boolean algebra identities that we can use to simplify logic equations. And you guys are probably already familiar with these identities. I'll quickly review them. So the identity law is that A or 0 equals A, right? Because we said that the OR operator is if one of the operands is 1, then the result is 1, otherwise is 0. So A or 0, this 0 here is not going to affect the result. If A is 1, then 1 or 0 will be 1, and if A is 0, then 0 or 0 will be 1. So A or 0 is always A. Similarly, A and 1 is always going to be A. This 1 doesn't affect the result of the AND. There's the 0-1 laws, which tell us that A or 1 is 1, right? Because the OR operator gives us a 1 if one of the operands is 1. So here, if I know already that one of the operands is 1, then trivially the result will be 1. And similarly, A and 0 will always be 0. Okay? Then we have the inverse laws. The inverse law tells us that A or not A is always 1. Right? Because if A was 1, then A not A is 0, and if A was 0, then not A is 1. So in this case, we're always going to have a 1 or 0, 1 on one of the sides of the one of the operands, so the result will be 1. And A and not A is 0 is always 0, because again, if A was 1, then not A will be 0, and if A was 0, then not A will be 1. So we will always have one of these be a 0. Other identities include commutative laws. So we know that A or B is equal to B or A, and A and B is equal to B and A. So these Boolean algebra operators are commutative. We have associative laws. Associative laws tell us that A or B or C is equal to A or B or C. So in which order we perform these OR operations doesn't matter. Similarly, for the AND operation, we know that A and B and C is equal to A and B and C. So again, in which order we apply these consecutive AND operators does not matter. And then finally, we have the distributive laws. The distributive laws tell us that A and B or C is equal to A and B or A and C. So in other words, we distribute this A onto the B and the C, so that we have an A and a B or an A and a C. And similarly, and this is a less intuitive one, A or B and C is equal to A or B and A or C. Okay, so these are the distributive laws. So let's see how we can. Oh, there's one more a very important law that I forgot about, the De Morgan's law. So what De Morgan's law tells us is that not A or B or C, etc. So we have if we have this OR operation across many variables, and then we have a not on top of this entire operation. This is equivalent to not A and not B and etc. and not C. And similarly, A and B and etc. and C, all of that inverted is equivalent to not A or not B or etc. or not C. Okay, so this is De Morgan's law. So let's look at how we can use these identities to simplify our logic equations. So this was the original logic equation that we got from this truth table, but we can actually simplify this further by applying the different logic identities. So for example, one thing we observe here is that D is common across these three terms. So what identity can we apply to simplify this further based on the observation that D is common? Right, somebody said factorize. I think you mean apply the distributive rule, exactly. So what we can do is we can take D out and we can have D and then we have the remaining parts of these terms, not K and L or K and not L or K and L. And then after that, we observe that K here is in common. So what we can apply the distributive rule again to factor out K. And then after that, we realize over here that we're left with not L or L. So what do we know about not L or L? So we know that not L or L is always going to be 1, exactly. So this is the inverse law. So here we're left with K and 1. And what do we know about K and 1? Right, K and 1 is always going to be K, exactly. So this is the identity law. So what we've done here is we've taken this logic equation up here and we've simplified it down to a simpler logic equation down here. Okay. So this is actually one way to simplify this logic equation, but we can actually simplify it in a different way. So if we apply different identities, we can take a different approach to simplifying this logic equation. So you'll see another observation. If we start from scratch, we'll notice that both of these terms at the beginning contain not K and L. So what can we do here? We can apply the distributive law to take out not K and L, and we'll be left with not D or D. And what do we know about not D or D? Right, not D or D is 1, and so we can remove it because it'll be not D or D is 1, then 1 and something is always that something. So we can apply the inverse law followed by the identity law. And then after that, we realize that D and K is common across these two terms, right? So we can apply the distributive law again, exactly. And when we do that, we're left with not L or L. And here we can apply the inverse and identity law again, and we get D and K. So you'll notice that starting from the same equation, we apply different identities to get different simplifications of this equation. And this is an important observation about the uniqueness of specification. So truth tables are unique, right? For a given a logic block, if I want to specify this logic block, the truth table is unique. There is only one unique truth table to specify a logic block. A different truth table means a different logic block. However, there are many different equations that can be used to specify the same functionality of a logic block. So a logic equation is not unique. Okay, so someone is asking if we ask you in a quiz or an exam, do you have to write down the names of the laws that you used? No, it's fine if you don't memorize the names of the laws, unless it's kind of a very important law like De Morgan's law. But it's fine if you don't memorize the names of the laws. Okay, so the important observation on this slide is that a truth table specification is unique, but a logic equation specification is not unique. We can have many different equations to specify the same logic block. Okay, so now let's move on to logic gates. So logic blocks are built from logic gates. We've seen logic gates before. So when we implement a logic block in a circuit, we use logic gates for this implementation. Any logic function can be implemented just like any logic operation can be specified using or, and not. Any logic function, any logic circuit can be implemented using three basic types of gates: the AND gate, the OR gate, and the NOT gate. And these are the symbols that we use for these gates. So if you see this gate over here, this is an AND gate, this over here is an OR gate, and this over here is a NOT gate. So for example, if I have this logic equation over here, D equals not A and B or not C, I can draw a logic diagram for this equation like this. We have this AND gate over here. We have not A and B. That's here, not A and B. And then here we have not C. And then we take this result and pass it through an OR gate. So here we get not A and B or not C, and that gives us D. Now, because these inverters are kind of a little bit tedious to draw, and we usually have inverters all over the place inside of a logic diagram, there's usually a shorthand for representing inverters, which is like this. We have these little bubbles at the inputs of our gates. So here, this bubble over here means not A and B, and this bubble over here means that the input coming in is not C. Okay, so these bubbles just make it easier for us to draw logic diagrams without having to draw these inverters, which are tedious to draw. Okay, any questions about logic diagrams? Okay, well then let's move on. So again, we'll visit uniqueness of implementation. So just like logic equations to specify the behavior of logic block are not unique, logic diagrams are also not unique. In other words, implementations of logic blocks are also not unique. And this gives us flexibility in implementing logic blocks. So for example, if I have these two different equations, each of these equations corresponds to a different logic diagram. In other words, each of these equations is going to correspond to a different way to implement the logic block. Now, obviously here, one way is better than another way, because here when I draw a logic diagram, all these AND gates and OR gates and NOT gates are going to correspond to actual hardware, same here. So in this case, which of these logic diagrams will use more hardware, the one on the left or the one on the right? Right, obviously the one on the left is going to be more expensive to implement in hardware because it has more gates. And what's actually more important than the number of gates, it turns out that the amount of circuitry that I need to implement a logic diagram actually corresponds to the number of gate inputs, right? Because a gate with 2 inputs needs less hardware than a gate with 10 inputs, for example. So the amount of circuitry that I need is, kind of loosely speaking, corresponds to the number of inputs into my logic gates. So let's do an example. So here I have a 3-input AND gate, and another 3-input AND gate, and another 3-input AND gate, and another 3-input AND gate. That's 3, 6, 9, 12. And I have a 4-input OR gate. That's 9 plus 4. That's 13. And then I have these inverters. So I have an inverter for D. That's 15. I have no, wait, I think I did the math wrong. So we have 3. These are 12, and then 12 plus 4. That's 7. 12 plus 4, that's 16. And then I have 3 inverters. I have an inverter for D, that's 17. An inverter for K, that's 18. This is another inverter for K, but we actually use just one inverter, so we don't have to double count this one over here. And then we have an inverter for L, so that's 19. Okay, so that's 19 total gate inputs. On the other end over here, we have here a 2-input AND gate and a 2-input AND gate and a 2-input OR gate. So 2 plus 2 plus 2 is 6. And then we have an inverter, so that's 7 total gate inputs. So here we have 19 total gate inputs. Here we have 7 total gate inputs. So you can tell that the circuit on the left actually requires more than it requires 19 over 7 times the hardware that the one on the right needs. So more than 2 times the hardware. Okay. So the challenge in implementing logic blocks efficiently is being able to find the circuit that gives us the smallest number of gate inputs. In other words, we want to be able to find the simplest logic equation to specify a logic block, so that the simplest logic equation translates into a circuit that uses the least amount of hardware. Okay, so the question is, how can we do this? Now, you saw earlier that the way that what we did is we applied these different these different Boolean algebra identities in different orders and arrived to different simplifications. What we would like to have is we would like to have a consistent way of us to be able to arrive at kind of an efficient implementation. And for this, what we're going to use is a tool called Karnaugh Maps. Okay, so what is a Karnaugh Map? A Karnaugh Map is essentially a technique for simplifying Boolean algebra expressions so they can be implemented with the smallest number of gates and inputs per gate. And the general approach of a Karnaugh Map is as follows. What we're going to do is we're going to take a truth table and we're going to lay it out on a 2-dimensional grid. And then after we do that, we're going to start searching for the largest rectangles in the grid whose sizes are a power of 2 until we cover all the ones in that grid. So let me give you an example. So here, let's say we had this truth table over here. We have 2 inputs to our logic block, A and B, and we have the output C. And here we have 1 in 3 of these cases and 0 in the other cases. So if we were going to write the logic equation directly from the truth table, we're going to get not A and not B, which corresponds to this row over here, 0, 0. And then the row 0, 1 is going to give us not A and B. And then the row 1, 1 is going to give us A and B. Okay, so this is the logic equation to represent this truth table specification of the logic block. But what we'd like to have is we would like to have a simpler equation so that we can have a simpler circuit. So let's see how we can do that. What we're going to do is we're going to draw a Karnaugh map like this. So what is a Karnaugh map? It's a 2-dimensional grid where we lay out our inputs on different dimensions. So here we're going to put A up here, and this column is going to correspond to an A is 0, and this column here is going to correspond to an A is 1. And then we're going to put B on this dimension, and this row is going to correspond to an B is 0, and this row here is going to correspond to an B is 1. And now what I'm going to do is I'm going to take the values in my truth table, and I'm going to use them to fill out the Karnaugh map. So here, when A is 0 and B is 0, C is 1. So here at 0, 0, C is going to be 1. So here, the value inside of the truth table here corresponds to C. When I have 0, 1, I also going to have 1. So here when A is 0 and B is 1, I'm going to have 1 in the Karnaugh map. And then when A is 1 and B is 0, I'm going to have 0. So here when A is 1 and B is 0, I'm going to put a 0 over here. And then finally, when A is 1 and B is 1, the output's going to be 1. So when A is 1 and B is 1, here the output will be 1. Okay, so now what I've done is I've used my truth table to fill out this Karnaugh map. Now what I'd like to do to simplify my equation is I want to search for the largest possible rectangles that I can use to cover all of the ones in this table. So let's start with this one over here. So I have this one over here. I can cover it with a square, but actually I can find a larger rectangle because this one is adjacent to this one down here. So what I can do is I can have a rectangle that covers both of these ones together. And I'm gonna put a rectangle here. This blue rectangle covers these ones. Now what I'm left with is I still need to cover this one with a rectangle. Now I could put just a square over this one on its own. However, we want to look for the largest possible rectangles because that will give us the most simplification. So here there's actually a larger rectangle that I can use to cover this one, which is this rectangle in green over here, which also covers this one over here. So it's okay that I covered this one on the left, this one over here twice. What I care about is using the largest possible rectangles to cover all my ones. So now that I've covered all the ones in the Karnaugh map, next what I do is I'm going to extract a term for each of these rectangles. So this blue rectangle over here covers both of these ones. So this blue rectangle is going to correspond to an A is 0. And here we don't care whether B is 0 or 1. So the term that we extract from the blue rectangle is not A. So in other words, the result is 1 whenever A is 0. Or we have the green rectangle. The green rectangle corresponds to when B is 1, regardless of what the value of A is. So here, the output's going to be 1 whenever B is 1. So here the simplification that we got from using the Karnaugh map is C is equal to not A or B. And as you can tell, this is a much simpler equation from the equation on the left, and it requires much less hardware to implement. Any questions about Karnaugh maps? Any questions about how we used Karnaugh maps to simplify this equation? I'll show larger Karnaugh maps in a little bit. We'll see how to use 3 variables and 4 variables maybe next time. Okay, if there are no questions, I'll move on to a larger example. Before that, so here again, a 2-variable Karnaugh map, we're going to have 0 and 1. We're going to have A on 1 dimension, B on 1 dimension, and then each of these squares, cells in the table is going to correspond to one of the terms in the bigger equation. Someone's asking, they don't get why not A is always 0. So let me kind of explain that again. Okay, so here the truth table tells us that C is 1 when A is 0 and B is 0. So the way that this translates into the equation is that here when A is 0, not A is going to be 1. And when B is 0, not B is going to be 1. So here, when A is 0 and B is 0, then not A and not B will be 1 and 1. So that will be 1. And then 1 or anything else is going to be 1. So in this case, C will be 1. So that is why here when we have A is 0 and B is 0, then C is 1. This will produce a term in our equation which is not A and not B. Okay. All right, so here in general, a 2-variable Karnaugh map, we have A on 1 dimension, B on the other dimension, and then here we're going to, each one of the cells is going to correspond to one of the terms in the truth table. Okay, now, and then if this column over here is going to correspond to A, this column is going to correspond to not A, this row here corresponds to B, and then this column, this row here corresponds to not B. Okay, so if I put a rectangle over this entire row, that will be not B. If I put a rectangle over this entire row, that will correspond to B. Now let's look at 3 variable Karnaugh maps. So 3 variable Karnaugh maps look like this. We only have 2 dimensions. So what we have to do is we're going to put A and B together on one of the dimensions and then C on the other dimension. Okay, but there's one important observation is that the order in which we put A and B on this dimension matters. So we're going to have 0, 0, 0, 1, and then we're going to have 1, 1, and then 1, 0. We're not going to do 0, 0, 0, 1, 1, 0, 1, 1 like we do in the truth table. This is referred to as gray code. So gray code, we're going to use gray code to order the combination of A and B on this dimension. And the reason the gray code, the important thing about gray code is that the variables, the bit sequence only changes by 1 bit at a time. Because here, if we're going to have 0, 1, and then 1, 0, that means there's 2 bits that are changing from this cell to this cell, and if we do that, the Karnaugh map won't work. But if we change 1 bit at a time, so here we go from 0, 1 to 1, 1, only this 0 is changing to a 1, which makes things work, and you'll see how. So here, these 2 columns together correspond to an A is 1, okay? Because here AB here is going to be 1, 1 or 1, 0. So for both of these columns, A is going to be 1. These 2 columns in the middle will correspond to when B is 1. And you'll notice that this is why it was important to only change 1 bit at a time using gray code. Because here we have 0, 1 or 1, 1. So in both of these cases, B is going to be 1. And then finally, this entire row over here corresponds to when C is 1. Okay? So now let's look at how we can use a 3 variable Karnaugh map to simplify a logic equation that has 3 variables as input. So this is another truth table. Here we have 3 inputs, A, B, and C, and an output D. And what we would like to do is we would like to find the simplest logic equation to express this operation that's specified by this truth table. So what we're going to do is we're going to lay out the truth table on the Karnaugh map. So here when A and B are 0, 0, so here A and B are 0, 0, C is going to be, when C is 0, D will be 0, and when C is 1, D will be 0. So we're going to put a 0 over here and a 0 over here. And then when A is 0 and B is 1, so here when A is 0 and B is 1, when C is 0, we'll have a 1, and when C is 1, we'll have a 1. So we're going to put a 1 and a 1 over here. And then next, when A is 1 and B is 0, then when C is 0 and C is 1, we will have a 1 and a 0. So one important thing to note here is that these 1 and 0 will not go in this column over here. They will go in this column over here. So that's a mistake that people frequently make. Because we're using gray code up here, 1, 0 is this column on the right. So here the 1, 0 over here will correspond to a 1, 0 over here. And then finally, when A is 1 and B is 1, then when C is 0, we will have D is 1, and when C is 1, D is 1. So we will put a 1, 1 over here. Okay. So if we're gonna do it quickly, you'll kind of get the hang of doing this quickly. So we have 0, 0, 1, 1, 1, 0, 1, 1. So we do 0, 0, 1, 1. Skip this column, do 1, 0 over here, then come back to this column and do 1, 1. And you'll get the hang of doing this quickly once you do some practice in the assignment. Someone's asking whether we can combine A and C on one dimension and put B on the other dimension. Yes, absolutely. You can do that. You can combine variables in any way that you like. It doesn't really matter because ultimately you will get the same result regardless of how you combine the variables. Okay, so now that we've laid out these variables on the Karnaugh map, what we would like to do now is we'd like to search for the largest possible rectangles to cover all the ones. So the largest rectangle that we can find first is this square over here. Remember, a square is a rectangle. So this square over here that covers these 4 ones. Okay, so this is one rectangle that we find. And then we're left with one more one that we need to cover. So we want to find the largest possible rectangle to cover this one. And that's going to be this rectangle over here. We're not just going to put a square over this one alone because we want to maximize the number of ones we cover to minimize the complexity of the equation. So we're going to use this rectangle over here to cover this one and this one as well. And it's okay that we covered this one twice. That doesn't matter. So one important observation here is we did not cover this one over here, right? We didn't put a rectangle over these 3 ones altogether. We only put a rectangle over these 2 ones. And the reason is that the rectangle has to be a power of, the size of the rectangle has to be a power of 2. That's important, okay? So now that we've done this, let's look for the equation that represents these 2 rectangles. So what does the blue rectangle represent?
It represents A bar and B plus A and B, or A and B.
Okay, so here the blue rectangle does not care if C is 0 or 1. But another important thing, for the blue rectangle, it does not matter if A is 0 or 1. It only matters that B is 1. So whenever B is 1, so this blue rectangle tells us that whenever B is 1, regardless of what C is and regardless of what A is, right, the D, the output will be 1. Okay, so whoever answered that was close. You're correct that C doesn't matter, but also this rectangle tells us that A doesn't matter. Okay, so here D is equal to B, which we get from the blue rectangle, or the green rectangle. What does the green rectangle tells us? The green rectangle tells us that here C matters, right? We're only going to, the green rectangle says is only covers the ones where C is 0, and then also A matters, right? So it only covers the cases where A is 1. So here, these 2 columns correspond to when A is 0, and these 2 columns correspond to when A is 1. So the green rectangle covers the case where A is 1. But over here, B doesn't matter. So here, B can be 1 or 0 for this green rectangle. And that's why the term here says that corresponds to the green rectangle is A and not C. Okay, in other words, when A is 1 and C is 0. And you can almost think of this as the intersection. So these 4 cells over here correspond to when A is 1, and then these 4 cells over here correspond to when C is 0. So the intersection of this row with these 2 columns is going to be this rectangle over here. Okay? All right, so now that we've seen how to use 3-variable Karnaugh maps, let's go back to our car warning system example. So here we had this truth table over here. Let's first fill out this truth table in the Karnaugh map. We're going to put a Karnaugh map. We're going to put D and K over here, and we're going to put L over here. And then we're going to fill it out. We have 0, 1, 0, 0, 0, 1, 1, 1. So we'll fill that out. We have 0, 1, 0, 0, and then we skip the 3rd column. We go here, the last one, we put 0, 1, and then we come back to the 3rd column and we put 1, 1. And now what we want to do is we want to look for the largest rectangles to cover our ones. So the first rectangle is going to be this column over here. So we're going to put a rectangle here. And then we have 2 more ones that we want to cover, this one over here and this one over here. And it turns out that we can actually cover these 2 ones with a single rectangle because the gray code wraps around, right? You can think of if you're in this column and you go to the right, it's as if you came back and wrapped around to this column over here. So we can actually do this. We can actually have one rectangle that starts with this one and then wraps around and goes back to this one over here. Okay, and by doing this, what we've done is we've covered our ones with 2 rectangles, and now what's left is to derive equations with a term for each of these rectangles. The blue rectangle corresponds to when D and K are 1, regardless of what L is. So here the blue rectangle corresponds to DK. And then the green rectangle corresponds to, I guess the answer is already on the slides. This is one of the drawbacks of using slides as opposed to explaining on the board. So here the green rectangle corresponds to when L is 1, so this row, and when K is 0. So you'll notice what this column, the fourth column, and the first column have in common is that for both of these columns, K is 0. This one is 0, 0, and this one is 1, 0. So D doesn't matter here, but K is 0 for both of these columns. Okay, so that's why the green rectangle corresponds to not K and L. And by doing this, we've got this simple equation, which corresponds, if you remember, we had multiple equations that we arrived to, and this was the simpler one. So here, using the Karnaugh map gave us the simpler equation to express the specification for this logic block. Okay. So with that, I end today's lecture. If you would like to refer to the textbook, you can refer to Appendix B, sections B.1 and B.2 to read more about the material we covered today. Okay. Anyone have any questions? Someone's asking if gray code is unique, or is it enough to ensure that there is only one bit difference between any two consecutive binary strings. I mean, when we say gray code, we usually refer to that specific way of changing ones between that specific way of changing ones between different variables. So yes, in that sense, gray code usually refers to a unique sequence. Okay, well, if there are no other questions, then that's all for today, and I'll see you next time. Bye, everyone.